In the polar world, a truck can fail long before its engine stops. The tires lose their grip. Snow hides a gap in the ice. Frozen ground turns soft without warning. And when the nearest workshop is hundreds of miles away, a routine breakdown can become a survival problem before another vehicle even knows where to look. That is why the machines in this countdown became so extreme. Some carry enough fuel and shelter to keep a crew alive for weeks. Some bend in the middle because a rigid truck would tear itself apart. Others abandoned wheels completely and replaced them with tracks. One machine stretched nearly 2 football fields. Another carried 8 people across Antarctica inside what looked like a railway carriage mounted on a tank. And the final vehicle had a laboratory, electric drive, and plans to carry a folding airplane on its roof. It had almost everything an expedition could ask for, except traction. These machines were not built for ordinary winter driving. They were created for the moment the road disappears, rescue becomes uncertain, and the vehicle itself may be the only warm place for hundreds of miles. The question is not which one has the biggest engine. It is which machine still makes sense when the cold, the distance, and the ground begin fighting back. Weak ice creates a problem that horsepower cannot solve. A heavy vehicle may have enough power to cross the Arctic, but if its weight breaks the surface beneath it, that power becomes useless. The machine has to carry fuel, tools, shelter, and a crew without pressing too hard against the ice. That problem shaped the Burlak. Developed in Russia as an amphibious snow and swamp vehicle, the Burlak is roughly 20 feet long and weighs around 4 tons, depending on configuration. That makes it relatively small beside the machines later in this list. Its 6 enormous low-pressure tires spread the vehicle's weight across a wide area, helping it move over snow that would swallow a conventional truck. Tire pressure can be adjusted from inside the cab as the surface changes from packed snow to loose powder. Then the ground disappears completely. The Burlak has a sealed body and can float, allowing it to enter open water between sections of ice. A propeller helps move it through the gap instead of leaving the crew trapped at the edge. That amphibious ability is not a novelty. In polar travel, an opening in the ice can divide a route with almost no warning. A normal truck stops. The Burlak enters the water and searches for another place to climb back onto the surface. Inside, the crew can sleep, cook, stay warm, and reach important mechanical systems without spending long periods exposed outside. Additional fuel gives expedition versions a range measured in thousands of kilometers. The Burlak's defining feature is not size. It is the fact that the same machine can leave solid ground, cross open water, and continue the journey without waiting for another vehicle to rescue it. It survives by carrying its own escape plan. The Burlak is built around a small expedition crew. The KAMAZ 6355 Arctic was designed around a much larger logistical problem. Remote industrial and research operations may need to move workers, fuel, tools, repair equipment, and heavy cargo into regions where the last real road ends hundreds of miles before the job site begins. A conventional long truck becomes difficult to steer in that environment. The front may already be climbing a ridge while the rear is still trapped in soft ground behind it. The KAMAZ solves that problem by bending in the middle. Its articulated frame allows the front and rear sections to turn relative to each other. That helps a vehicle nearly 40 feet long follow the terrain instead of forcing one rigid chassis through every change in direction. 8 driven wheels keep the machine pulling when different axles are dealing with completely different surfaces. Behind the cab, the chassis can carry cargo, cranes, workshop equipment, fuel systems, or insulated living modules. In some configurations, it is less like a truck delivering supplies and more like a mobile worksite arriving in one piece. That matters because remote crews cannot assume another service vehicle is waiting nearby. If a machine breaks down, the tools needed to repair it may have to arrive on the same vehicle carrying the mechanics, the shelter, and the replacement parts. The KAMAZ is slow, expensive, and far too specialized for ordinary roads. But ordinary roads are not where it earns its place. Its defining image is 2 massive sections moving at different angles, the front already escaping while the rear is still fighting the ground. During the Cold War, the United States and Canada wanted a chain of radar stations stretching across the far north. On a map, That looked like a line. On the ground, it meant carrying generators, antennas, communication equipment, fuel, and construction material into territory where the freight system ended long before the building site began. The FWD MM-1 Terracruiser was developed during the 1950s to help solve that problem. Its job was to tow critical radar and support modules across northern Canada and Alaska. These were not ordinary trailers carrying replaceable cargo. Without the generator, the radar could not operate. Without the antenna module, the station was incomplete. Without the station, part of the warning line existed only on paper. The MM-1 measured roughly 33 feet long and rode on tires more than 5 feet tall. A gasoline V8 produced around 400 horsepower through an all-wheel drive system. But the machine was not important because of the engine under its hood. It was important because of what followed behind it. Picture the final road ending at the edge of frozen wilderness. From that point forward, every steel frame, cable spool, generator, and radar component still had to move. Mud, snow, and frozen wetlands did not care that the equipment was part of a national defense system. The Terracruiser had to make the final miles possible. Temperatures could fall below -50 degrees Fahrenheit. Batteries weakened. Fluids thickened. Rubber seals became less forgiving. A machine that started easily in a heated workshop could behave very differently after a night exposed outside. The MM-1 helped carry the pieces of the early warning network into places ordinary logistics could barely reach. The truck disappeared from the story once the construction was complete. The radar stations it helped place did not. 6 tires do not sound excessive. Then each one rises more than 5 feet from the ground, and 2 separate engines begin working beneath the body. The ZIL E-167 was a Soviet experimental vehicle developed in the early 1960s for deep snow, frozen swamps, forest routes, and Siberian tundra. It stretched more than 26 feet and measured nearly 10 feet wide. The body resembled a military carrier, but the enormous wheels made it look closer to a rover built for ground that had forgotten how to behave like ground. 2 gasoline V8 engines produced a combined output of roughly 360 horsepower. Each engine helped drive part of the 6-wheel system, giving the vehicle an unusual mechanical layout even by Soviet prototype standards. The E-167 was not limited to a factory yard. It covered thousands of miles during tests through snow, forest, and frozen rivers. The machine entered the exact environment that had justified its existence, and it proved capable of continuing where conventional trucks lost mobility. Its heated and insulated cabin kept a small crew functioning in temperatures far below zero. Cold start equipment allowed both engines to wake after long exposure to winter conditions. Technically, the idea worked. Then the fuel bill arrived. 2 engines meant 2 systems consuming gasoline, 2 powertrains adding complexity, and twice as many opportunities for something difficult to repair far from a workshop. The E-167 proved that engineers could build a vehicle capable of crossing extreme Siberian terrain. It never proved that an industry could afford to build and operate an entire fleet. The machine survived the wilderness. The project did not survive the operating cost. Wheels work until the surface becomes too soft to support them. The Ural 5920 answered that problem by removing the wheels completely. Its cab and cargo deck still resembled a truck, but beneath them sat 2 long-tracked units, joined through an articulated center section. The machine could bend in the middle to turn. That allowed an 11-meter vehicle to maneuver through tundra, wetlands, deep snow, and soft industrial ground without steering like a conventional tank. The tracks were not designed for speed. They were designed to prevent the vehicle from digging itself into the surface it was trying to cross. The Ural weighed roughly 13 tons and could carry around 5 tons of cargo. Its diesel engine produced modest power compared with the twin-engine ZIL, but horsepower was not the main advantage. The tracks converted that power into steady movement at low speed. Oil and gas crews used vehicles of this type to carry supplies and equipment into places where wheeled trucks could no longer continue. Heated cabs, engine warmers, and basic sleeping space helped crews work far from permanent facilities. Its limitation was obvious. Tracks made it capable in soft terrain, but slow, mechanically demanding, and unsuitable for ordinary highway travel. The same system that saved it in the tundra made it inconvenient almost everywhere else. The Ural did not try to become a better truck. It accepted that the truck layout had already failed and became something closer to a cargo crawler. The Rolagon did not look like the product of one clean engineering program. That was because many of them were not. Catco crews built and modified these vehicles using parts taken from tractors, buses, trucks, and heavy industrial equipment. The result looked improvised because it was improvised, but on a scale large enough to carry more than 30 tons. The most recognizable feature was the tires. Some measured close to 8 feet tall and visibly sagged beneath the load like giant rubber drums. They looked too soft to support a machine that heavy. That softness was exactly the point. The Rolagon was designed for snow, tundra, and permafrost that could be badly damaged or simply broken through by narrower tires. Instead of attacking the surface, the machine rolled over it with tires that deformed around the ground. But the real story was not the physics. It was the way crews turned that principle into working transport. There was no single perfect Rolagon configuration. Different jobs required different engines, cabins, frames, wheel arrangements, and cargo systems. Some used 6-wheel drive, others used 8. Caterpillar diesel components were common, but the final machine often reflected whatever the operator needed and whatever the builders could make work. These vehicles carried fuel, communication equipment, construction material, and supplies into isolated areas across Alaska and northern Canada. They were industrial tools, not polished prototypes. A damaged component might come from a truck. Another might have started life on a bus. The frame could be altered again when the next job demanded something different. The Rolagon's memory image is not a laboratory drawing. It is a group of mechanics assembling a frozen country hauler from parts that were never originally meant to become one machine. The Crest AHT 730C was built for towing operations, where losing control could mean watching hundreds of tons slide in a direction the driver never chose. This articulated 6-wheel drive tractor was used for heavy work in northern regions, including operations in Canada, Alaska, and polar research environments. A Caterpillar diesel produced roughly 370 horsepower. That power could begin the movement. Stopping it required a different set of systems. The tractor used heavy braking equipment and an engine retarder to control the load without depending entirely on the wheel brakes. On ice, simply locking the wheels can remove the little steering control the driver still has. The goal is not maximum braking force at once. It is controlled resistance. The articulated chassis lets the front and rear sections follow the turn instead of forcing one long frame through it. A hydraulic winch gives the crew another option if the tractor or trailer begins sliding or becomes trapped. Then the cold begins attacking everything around the drivetrain. At temperatures near -76 degrees Fahrenheit, fluids thicken. Batteries lose strength. Hoses, seals, and electrical systems become less forgiving. A machine that works perfectly in a heated building may respond much more slowly after spending the night outside. Cold start equipment helps bring the engine back to life. The heated cab protects the operator from fatigue, numb hands, and the kind of poor decision that can turn a difficult recovery into a disaster. The Crest is not memorable because it pulls the heaviest load in the video. It is memorable because it has to keep that load behind it. Hundreds of tons pushing downhill, limited traction beneath the tires, and one tractor responsible for preventing the convoy from becoming an uncontrolled slide. In Antarctica, a vehicle may spend days traveling between permanent stations. That means it cannot simply carry the crew. It has to replace the building they left behind. The Kharkov-Chanka was developed in the Soviet Union during the late 1950s using the platform of the ATT heavy tractor, which itself had roots in tank technology. It measured roughly 28 feet long, more than 11 feet wide, and stood about 13 feet high. Wide tracks carried a body that looked less like a vehicle than a railway carriage placed on a tracked chassis. Inside were bunks, heating, communication equipment, a kitchen, workspace, storage, and room for a crew of up to 8. The first machines traveled from the Antarctic coast toward Vostok Station. In December 1959, 2 Kharkovchankas and an additional tractor continued from Vostok toward the geographic South Pole. They arrived on December 26. That journey transformed the machine from an unusual design into a working polar base. The crew could travel, sleep, communicate, prepare food, conduct repairs, and continue scientific work without depending on a permanent structure every night. The original version placed the engine inside the main body, so the crew could service it without stepping into Antarctic weather. That solved one problem and created several smaller ones. The engine produced noise, heat, exhaust, and soot inside the same structure where the crew was expected to eat and sleep. Nobody on board was likely to forget that their house had a diesel engine sharing the floor plan. Later versions improved the arrangement. But the original Kharkovchanka had already proved the central idea. In Antarctica, the successful vehicle was not merely the one that crossed the snow. It was the one that carried enough civilization to keep the people inside functioning after the horizon had erased everything else. A truck can carry supplies. The Overland Train Mark II attempted to carry the entire supply system. Developed for the United States Army during the late 1950s, the machine was designed to move large amounts of cargo across Arctic terrain without relying on roads, rails, ports, or constant aircraft support. A command unit pulled 7 connected trailers. Together, the machine stretched 173 meters, nearly 2 football fields from end to end, and could transport more than 150 tons of cargo. The propulsion system made the design even stranger. A turbo diesel engine generated electricity, and that power was distributed to motors at the wheels. Instead of relying on one tractor to drag every dead axle behind it, driven wheels along the train helped move the full system through snow and frozen ground. Each tire stood roughly 8 feet tall. The elevated command cab gave the crew a view across the convoy and included heating, navigation, and radio equipment for isolated operations. The machine was tested for Arctic logistics, including the enormous problem of supplying early warning installations across remote northern territory. At full length, the overland train no longer resembled a truck towing trailers. It looked like a freight railroad that had removed the rails and decided to carry its own route. That scale also created the weakness. The system was expensive. Turning, fueling, repairing, and coordinating a vehicle nearly 2 football fields long required an entire operation. Then, heavy-lift aircraft improved. Once aircraft could move major cargo directly into remote areas, the reason for operating a 173-meter land train began to disappear. The overland train succeeded technically. It moved. The world simply found a less complicated way to move the cargo. The final machine had almost everything: living quarters, a research laboratory, heating, food and fuel storage, electric motors at the wheels, retractable wheels, and a plan to carry a small airplane on its roof. The Antarctic Snow Cruiser was designed in the United States in 1939 as a mobile research base, capable of crossing the continent for months without conventional support. It was 55 feet long, nearly 20 feet wide, and weighed around 75,000 pounds. 4 smooth tires stood 10 feet tall. 2 diesel engines generated electricity for 4-wheel motors. Inside, the crew had sleeping and working space, a darkroom, storage, controls, and scientific equipment. On paper, the snow cruiser combined transportation, shelter, aviation, and research into one extraordinary machine. Its journey toward Antarctica created trouble before it even reached the ice. During the drive from Chicago to Boston, a steering problem sent the giant vehicle partly off a bridge in Ohio. It remained stuck for several days before the journey could continue. That should have been a warning. When the cruiser arrived in Antarctica in January 1940, the crew built a timber ramp to unload it from the ship. One wheel broke through the ramp. The machine managed to power itself free. Then it entered the snow. The enormous smooth tires spun almost uselessly. They sank into the surface and generated far less traction than engineers had expected. The crew tried adding the 2 spare wheels to the front axle. They fitted chains to the rear tires. The cruiser still refused to behave like the Continental Explorer shown in the plans. Then the crew discovered something absurd. The tires gripped better when the vehicle drove backward. The snow cruiser's longest journey covered 92 miles, entirely in reverse. A machine designed to cross Antarctica while carrying a laboratory and an airplane achieved its greatest mobility by turning its back on the direction it was supposed to travel. The project did not become completely useless. Crew members lived inside the stationary vehicle and used it as a base for scientific work. But the grand crossing never happened. As the United States shifted its attention toward World War II, funding disappeared. The cruiser remained on the ice. It was found again years later, buried beneath snow but still recognizable. After shifting ice and later expeditions changed the landscape, the machine disappeared from view. Its final location remains unknown. It may still be buried within Antarctic ice, or the section supporting it may have broken away and carried it into the ocean. That uncertainty gives the snow cruiser its final image. Engineers built a mobile laboratory to master Antarctica. Antarctica may have removed it from the map. The polar world does not care how much a machine costs, how advanced it looks, or how confidently it was designed. It rewards the vehicle that can keep moving, and quietly buries the one that cannot. Which of these machines would you trust when the road, the weather, and the nearest rescue have all disappeared? Tell us below. And subscribe to Megamass for more machines built to enter places ordinary engineering was never meant to survive.